There are 40 billion Earth-sized planets in the habitable zones of our galaxy. 40 billion places where liquid water could pool, where chemistry could turn into biology. 65 years of searching every one we can reach has produced a single result: zero. We are going to trace that zero through 76 years of investigation, from a lunch table at Los Alamos to a signal that screamed for 72 seconds and never came back, to the economists and physicists who think they know what is killing every civilization before it gets loud enough for us to hear. You will see telescopes demolished for golf courses, a Russian astronomer who broadcast humanity's location without asking anyone, and 2 papers published in the last 2 years that place the Great Filter directly ahead of us. In March of 2020, after 21 years of continuous operation, SETI at home quietly shut down. The project had used millions of volunteer computers around the world to sift through radio telescope data, searching for patterns that might indicate an intelligent signal from somewhere beyond Earth. Over 2 decades, those computers processed 12 billion candidate signals. 12 billion. Every single one turned out to be noise. Not one confirmed extraterrestrial transmission. The final result, after all that time and all that computing power, was 0. That number deserves a moment. 65 years of formal searching, starting with a single radio telescope in West Virginia in 1960 and extending through some of the most powerful instruments ever built. Thousands of scientists across dozens of countries. Hundreds of millions of dollars in funding, mostly private, because the United States government stopped paying for this work in 1993. And the answer, as of early 2026, is still 0. This is not a failure of effort. The Breakthrough Listen program alone has scanned approximately 1 million nearby stars and accumulated more than 2 petabytes of data. The cosmic system on the Very Large Array observed over 950,000 unique fields in its first 11 months of operation. The Murchison Wide Field Array surveyed 2,800 entire galaxies. Every search, every instrument, every frequency band returned the same result: nothing. The number of places where life could exist keeps climbing at the same time. As of early 2026, astronomers have confirmed more than 6,000 exoplanets. Statistical models built on data from the Kepler Space Telescope estimate roughly 40 billion Earth-sized planets sitting in habitable zones across the Milky Way alone. 40 billion potential homes for life in just one galaxy, and the observable universe contains at least 2 trillion galaxies. Think about that ratio: 40 billion possible Earths in our galaxy. 0 signals detected. If you spread those 40 billion planets across the Milky Way's disk, one would sit within roughly every 2 light-years of another. That is denser than the spacing between most stars. The real estate is not the problem. So the most expensive, most extensive search in human history has produced a single data point, and that data point is 0. Some people treat this as a non-result, a shrug, an absence of information. It is the opposite. 0 is a measurement. It is the most important measurement in the history of the search for extraterrestrial intelligence. 60 years of accumulated null results run through statistical models now constrain the number of detectable technological civilizations in the Milky Way to fewer than 1 to 5 per century. That is not a guess. That is what the data says. The question this investigation follows is simple to state and very difficult to answer. If life starts easily, and planets are everywhere, what is killing every civilization before it can reach us? Something is filtering them out. Something is stopping the galaxy from filling up with signals and spacecraft and evidence of engineering. The universe has had 13.6 billion years to produce neighbors. It produced us. As far as we can tell, it produced nobody else. That is the starting point. The silence is not empty. It is full of information, and the information is unsettling. To understand why, you have to go back to a cafeteria in New Mexico, a summer afternoon in 1950, and a question asked over lunch that still has no answer. The Los Alamos National Laboratory, summer of 1950. 4 physicists are walking to lunch: Enrico Fermi, Edward Teller, Herbert York, and Emil Konopinski. The conversation is light. Someone mentions a recent New Yorker cartoon about flying saucers. There have been a string of UFO reports in the news, and the 4 men joke about them as they sit down to eat. Then, mid-conversation, Fermi asks a question that stops the table. Where is everybody? The other 3 understand immediately what he means. Fermi was asking about mathematics. The Milky Way contains somewhere between 200 billion and 400 billion stars. It is roughly 13.6 billion years old, a technological civilization expanding at just 1% the speed of light, a pace far below anything exotic, could cross the entire galaxy in 10 to 100 million years. That sounds like a long time, until you compare it to the age of the galaxy itself. 100 million years is less than 1% of the Milky Way's lifespan. There has been enough time for this to happen thousands of times over. Fermi did back-of-the-envelope calculations right there at the table. The numbers were not close. They were not ambiguous. Even with conservative assumptions about how many stars have planets, how often life arises, and how long civilizations last, the galaxy should be crawling with evidence of intelligent activity, spacecraft, signals, engineering on a scale visible across interstellar distances. There should be something. There was nothing. The question landed differently from a normal scientific puzzle. Most problems in physics have a clear path to investigation. You build an instrument, you run an experiment, you collect data. But Fermi's question pointed at an absence, and absences are harder to study. You cannot point a telescope at silence and learn why it exists. The question sat in the air, unresolved, for the rest of lunch. It sat unresolved for the rest of the decade. Michael Hart formalized the argument in a 1975 paper, laying out the logic rigorously. If interstellar travel is possible even at low speeds, and if civilizations arise with any regularity, the galaxy should already be colonized. The fact that it is not requires an explanation. Every proposed answer to that question now carries Fermi's name. Even though he never wrote the argument down himself, he simply asked, and nobody could answer. To get a sense of the timescale problem, consider this. If you compress the entire history of the Milky Way into a single calendar year, with the Big Bang on January 1st and today on December 31st, 100 million years would be roughly 2.5 days. A colonization wave moving at 1% light speed would cross the galaxy in a long weekend. The galaxy has had the equivalent of 365 days. The universe had time, it had space, it had the raw materials. Every generation of stars produced heavier elements, seeding the next generation with more complex chemistry. Fermi's question was not rhetorical. He expected an answer. He expected someone to point out the flaw in the logic. Nobody did. And for 10 years after that lunch, the question just sat there, because nobody had the tools to look. Then one man decided to stop asking and start listening. April 8th, 1960. A 29-year-old astronomer named Frank Drake points the 85-foot Tittel telescope at Green Bank, West Virginia, toward 2 nearby stars, Tau Ceti and Epsilon Eridani. He tunes to 1420 MHz, the emission frequency of neutral hydrogen, the most abundant element in the universe. Giuseppe Cocconi and Philip Morrison had proposed this frequency in a 1959 paper in Nature, arguing it was the logical channel for interstellar communication. Any technological civilization would know about the hydrogen line. It was the obvious place to listen. Drake called it Project Ozma, after the Queen of the Land of Oz. Over roughly 150 hours, he listened. At one point, a strong pulsing signal came through and the team froze. It turned out to be a high-altitude aircraft. After that false alarm, the rest was silence. Ozma found nothing. But Project Ozma carried an assumption that would take decades to correct. Drake and nearly everyone in the field believed planets were uncommon. When Drake convened a conference at Green Bank in November of 1961 to formalize the search, 10 attendees, including Carl Sagan, worked through what became known as the Drake equation. It was not really an equation in the mathematical sense. It was a framework, a way of organizing ignorance. You multiply the rate of star formation by the fraction of stars with planets, by the fraction of those planets that could support life, by the fraction where life actually develops, by the fraction where intelligence arises, by the fraction that build detectable technology, by the average lifespan of such civilizations. The second variable, the fraction of stars with planets, was designated FP. Drake and his colleagues set it at 0.2, 1 in 5. It was a guess, and it felt generous at the time. Many astronomers thought planetary formation might require unusual conditions. They were wrong by a factor of 5. Between 2009 and 2018, NASA's Kepler Space Telescope stared at roughly 150,000 stars and watched for the tiny dips in brightness caused by planets crossing in front of them. Kepler confirmed 2,783 exoplanets. The statistical analysis that followed upended the field. Virtually every star in the Milky Way has at least one planet. The fraction FP went to effectively 1.0. Every star. To understand what that did to the math, take the Milky Way's estimated 200 to 400 billion stars and multiply by 1 instead of 0.2. The number of planets jumped by a factor of 5 overnight. Further analysis of Kepler data estimated roughly 40 billion Earth-sized planets orbiting within the habitable zones of their stars in our galaxy alone. 40 billion worlds where liquid water could exist on the surface. That is roughly 5 planets for every human being alive today. This was supposed to be good news. More planets means more chances for life, more chances for civilizations, more chances for contact. Instead, it made the silence catastrophically worse. If the real estate was always this abundant, the question was no longer, are there enough planets? The question became, with 40 billion potential homes, why is nobody there? Every new exoplanet discovery tightened the paradox. The galaxy was not short on places for life to begin. Something else was stopping it. And 7 years after Ozma, a graduate student accidentally found something that everyone initially thought was the answer. 1967, Jocelyn Bell Burnell, a graduate student at Cambridge, is analyzing data from a radio telescope designed to study quasars. She notices a signal, a rapid, precise pulse repeating every 1.337 seconds. Nothing natural was known to pulse with that kind of regularity. The research team labels the source LGM1. Little green men, they are half joking, but only half. For weeks, the possibility of an artificial origin sits on the table. Belle Burnell and her supervisor, Anthony Hewish, consider it seriously. Then a second pulsing source is found in a different part of the sky, and then a third. The explanation turns out to be rotating neutron stars, collapsed stellar cores spinning at extraordinary speeds, and sweeping beams of radio energy like a lighthouse. The signals are natural. They are called pulsars. The episode mattered for 2 reasons. It demonstrated that the universe produces phenomena that mimic intelligence with uncomfortable precision. A perfectly timed pulse, repeating without variation, looks designed. It was not. Nature can be deceptively regular, and that lesson would become relevant again and again over the following decades. Because the history of searching for extraterrestrial intelligence is largely a history of false pattern recognition. 10 years after LGM-1, on August 15th, 1977, the opposite happened. Jerry Eman, a volunteer astronomer working with Ohio State University's Big Ear radio telescope, was reviewing data printouts the following day. Big Ear was a flat reflector telescope that scanned strips of sky as Earth rotated. The data came out on continuous paper, columns of alphanumeric characters representing signal intensity at different frequencies. One sequence jumped off the page. At exactly 1420.726 MHz, the hydrogen line, a signal appeared that was roughly 30 times louder than the background noise of space. The peak intensity exceeded 250 Janskis. It lasted 72 seconds, which was exactly how long a celestial source would remain in Big Ear's beam as Earth turned. The signal behaved exactly the way an extraterrestrial transmission should behave. Eman circled the character sequence 6EQUJ5 and wrote a single word in red ink in the margin, "Wow." To put 250 Janskis in physical terms, imagine the difference between a whisper and a shout in a quiet room. The cosmic background at that frequency is the whisper. The wow signal was someone shouting directly into the microphone, at exactly the frequency that Cocconi and Morrison had identified in 1959 as the Universal Communication Channel. The signal never repeated. Eman and others pointed Big Ear at the same patch of sky hundreds of times over the following years. Nothing. Other telescopes searched the same coordinates. Nothing. The signal came from the direction of the constellation Sagittarius, from a region with no remarkable star or object. For the next 40 years, the WOW signal sat as the single strongest candidate for an extraterrestrial transmission in the history of SETI. One burst, 72 seconds, then silence. It was the opposite of LGM, 1 inch every way. Pulses repeated and turned out to be natural. The WOW signal appeared once and defied natural explanation. What happened to it, and to the telescope that detected it, forms one of the strangest chapters in all of science. The Big Ear Radio Telescope operated from 1963 until it was demolished sometime between 1997 and 1998. The land in Delaware, Ohio, was sold to a developer. The developer built a golf course. The instrument that captured humanity's most compelling candidate for an alien signal was torn down so people could play 18 holes on the ground where it stood. If you visit that spot today, there is nothing to indicate what once listened to the sky from that location. The WOW signal, through all of this, remained unexplained. Dozens of hypotheses circulated over the decades. Satellite interference, a classified military transmission, an equipment glitch, none fit. The frequency was too precise, the behavior too consistent with a deep sky source, the intensity too high for any known terrestrial or orbital origin. Then, in 2017, Antonio Paris, an astronomer at St. Petersburg College, proposed an answer that seemed to close the case. Two comets, designated 266P Christensen and P2008Y2, had been in the general area of Big Ear's beam on the night of August 15, 1977. Paris argued that hydrogen clouds surrounding these comets could produce emission at 1420 MHz, mimicking the exact signal Eman detected. Comets do carry hydrogen. The frequency matched. Several media outlets reported the mystery as solved. The explanation was comfortable. It gave the WOW signal a natural origin. It allowed the broader scientific community to move on. And for a few years, many people did. The comet hypothesis entered popular science articles and YouTube videos as the accepted explanation, except there were problems from the start. Other astronomers pointed out that the comets in question were not actually in the correct beam position on that date. Big Ear had 2 feed horns, and the geometry did not place either comet in the right one. More fundamentally, comets emit radio signals at 1420 MHz at extremely low power. The kind of emission a hydrogen cloud around a small comet can produce is many orders of magnitude weaker than 250 Janskis. It is like proposing that a candle caused a forest fire visible from orbit. The scale was wrong. For context on what 250 Janskis means at that frequency, consider that the entire WOW signal delivered more energy to Big Ear's receiver in 72 seconds than any known comet has ever produced at radio wavelengths in recorded observation. A comet producing that signal would need a hydrogen envelope roughly the size of a small planet, radiating in a way no comet has ever been observed to do. The debunking of the comet hypothesis happened gradually. Multiple researchers published critiques between 2017 and 2018, but the debunking never got the same attention as the original claim. In popular culture, the comet explanation stuck. It was clean. It was simple. It let people stop wondering. Then, in 2025, a team decided to go back to the beginning, straight to the paper. The actual physical printouts from Big Ear's observation run in August of 1977, 75,000 pages of dot matrix output, sitting in archives for nearly half a century. Nobody had done a full systematic reanalysis of the original data in decades. The results destroyed the comet hypothesis and replaced it with something nobody expected. The 2025 reanalysis was painstaking. Researchers used optical character recognition to digitize over 75,000 pages of Big Ear's archival dot matrix printouts from the 1970s. These were the original data records, the raw output of the telescope's receiver system. Nobody had conducted a full systematic review of this volume of material since the signal was first detected. The results confirmed what Eman had seen that night, but with greater precision. The WOW signal's flux density exceeded 250 Janskis. At that power level, the comet explanation collapses completely. Comets at 1420 MHz produce emission measured in millijanskis, thousands of times below the observed intensity, and the positional analysis confirmed what critics had argued for years. Neither Comet 266P Christensen nor P2008Y2 was actually located in the correct feed horn beam on that date. The geometry was wrong. The power was wrong. The comets could not have produced this signal. So if it was not a comet, and it was not terrestrial interference, and it was not a satellite, what was it? The new best hypothesis is stranger than any of those explanations, and stranger than aliens. Researchers now propose that the WOW signal was a rare superradiance event, also described as a hydrogen mesa flare, possibly triggered by a magnetar. In plain terms, under specific and unusual conditions, a cloud of cold hydrogen gas can be stimulated to emit a sudden, intense burst of radiation at exactly 1420 MHz. If a magnetar, a neutron star with an extremely powerful magnetic field, passes near or through such a cloud, it can trigger this kind of coherent emission. The result is a one-time cosmic belch of perfectly tuned radiation, powerful, brief, non-repeating. This explanation fits every observed characteristic. The frequency is exactly right because the emission comes from hydrogen itself. The intensity is consistent with superradiance amplification, which can produce enormous power from a relatively small cloud. The 72-second duration matches the beam transit time, meaning the source appeared to be at a fixed point in the sky, and the non-repeating nature makes sense because superradiance events are rare and depend on a specific alignment of conditions that may never recur at the same location. To make the scale tangible, imagine a balloon filled with gas that has been slowly pressurized for thousands of years. One day, a spark hits it. The balloon does not pop slowly. It releases all its energy in a single flash. Then it is gone. The conditions that built it up no longer exist. You could watch that spot in the sky for another 50 years and never see it again. The WOW signal was not intelligence. It was not comets. It was something the universe produced naturally but so rarely that nobody had predicted it. The cosmos generated a signal that perfectly mimicked what we expected from an alien civilization at exactly the frequency we were listening on, and it did so through raw physics. This mattered beyond the WOW signal itself. It established a pattern that would repeat throughout the history of SETI. Every time scientists believed they had found evidence of technology, the universe offered a natural explanation that no one had anticipated. Pulsars mimicked regular transmissions. comets were blamed, and then cleared. Superradiance produced a perfect fake. And the question got harder. If the universe keeps generating false positives that look exactly like intelligence, how would we recognize the real thing if it ever appeared? Go back to the Drake equation and look at what happened to every variable scientists could actually measure. In 1961, the fraction of stars with planets was guessed at 0.2. Kepler proved it was closer to 1.0. The rate of star formation in the Milky Way was estimated at 1 per year. Modern observations put it between 1.5 and 3. The number of potentially habitable planets was thought to be small. It turned out to be 40 billion in our galaxy alone. And then there is abiogenesis, the origin of life from non-living chemistry. Earth formed approximately 4.54 billion years ago. The last universal common ancestor of all life on Earth, known as Luca, existed roughly 4.2 billion years ago. The gap is only 300 to 400 million years, and much of that early period the surface was molten, bombarded by asteroids, essentially uninhabitable. Life did not wait for ideal conditions. It appeared almost as soon as conditions allowed, possibly sooner. If abiogenesis is easy, and every piece of evidence from Earth suggests it is, then life should be common across the galaxy. Every measurable variable in the Drake equation has moved in the optimistic direction since 1961. More stars have planets. More planets sit in habitable zones. Life starts faster than anyone expected. The galaxy should be teeming. The result of 65 years of searching is 0. That means the filter must sit at one of the variables we cannot yet measure. In 2024, Stern and Guerrier published a paper that targeted one specific variable, phi, the fraction of planets with life that go on to develop intelligence. Drake's original estimate treated phi as close to 100%. If life starts, evolution is relentless. Given enough time, something smart will emerge. Intelligence seemed like a natural endpoint. Stern and Guerrier argued it is not. Their analysis estimated phi at between 0.003% and 0.2%, between 3 in 100,000 and 2 in 1,000. Their reasoning was geological. Intelligence on the scale that leads to technology requires a very specific planetary configuration. You need 500 million years or more of continuous plate tectonics. You need a particular ratio of continent to ocean that allows complex ecosystems to develop on land. You need geological stability over timescales that most planets simply do not provide. To make that probability tangible, consider a jar filled with 100,000 marbles. Under Stern and Guerrier's lower estimate, 3 of those marbles represent planets where life develops intelligence. Under their upper estimate, 200. Compared to Drake's original assumption that nearly all 100,000 marbles would qualify, the difference is staggering. If intelligence is that rare, the silence starts to make more sense. 40 billion habitable planets sounds like an enormous number until you multiply it by 0.003%. That gives you roughly 1.2 million planets with intelligent life across the entire Milky Way, spread across 13.6 billion years of history. Divide by the galaxy's lifespan, and the number alive at any given time shrinks to almost nothing. But there is a problem with pinning everything on the intelligence bottleneck, because the very foundation of the rare Earth argument, the thing Stern and Guerrier depend on, may not work the way anyone thought. In 2000, Peter Ward and Donald Brownlee at the University of Washington published Rare Earth, a book that became one of the most influential arguments for why we might be alone. Their case rested on a chain of requirements. Complex life needs a stable climate. A stable climate needs plate tectonics to regulate carbon dioxide, recycle nutrients into the biosphere, and help maintain a planetary magnetic field. Plate tectonics requires a specific internal heat budget and a mantle of the right composition. Earth has all of these. Most planets probably do not. The argument was elegant. We are rare because our geology is rare. For 15 years, rare Earth was the standard, we are special explanation. It fit neatly with the Fermi Paradox. If plate tectonics are an unlikely accident, and if intelligence requires plate tectonics, then the great filter is geological. We passed it. We are on the lucky side. Then the models started to disagree. Computer simulations conducted between 2015 and 2024 gradually undermined the neat causal chain. Some models showed that plate tectonics on Earth might not have preceded the emergence of complex life. Instead, tectonics may have arisen partly because of complex life. Biological activity on the surface, particularly the weathering of rocks by organisms, may have weakened the crust enough to allow subduction to begin. If true, the relationship is backwards. Life does not need tectonics. Tectonics need life. Other simulations produced a different problem. Some models showed that plate tectonics can actually slow oxygenation of the atmosphere because subduction pulls oxidized material back into the mantle. If the process that was supposed to make complex life possible is actually delaying it, the rare Earth framework loses a critical load-bearing wall. Then there was Pluto. When NASA's New Horizons spacecraft flew past the Pluto system in 2015, it sent back images of geological activity that nobody expected. Pluto's surface showed evidence of icy tectonics, with fractured plates and what appeared to be convective overturn in a nitrogen ice glacier called Sputnik Planitia. The region spans roughly 620 miles across, an area larger than the state of Texas. Charon, Pluto's largest moon, showed similar features. These are worlds billions of miles from the nearest star's warmth, receiving about 1/1000th the solar energy Earth gets. Nobody predicted active geology there. The discovery did not prove plate tectonics are common, but it demonstrated that geological activity can arise in conditions far outside the narrow window that rare Earth proposed. None of this disproves the idea that intelligence requires specific geology. It complicates it. The clean story, where a rare type of tectonic activity on a rare type of planet produces a rare type of biosphere, keeps getting messier with each new model and each new observation. The requirements for intelligence might still be steep, but they might not be the requirements we listed. If tectonics are not the rare ingredient, and planets are everywhere, and life starts fast, the investigation circles back to the original problem. Something is filtering civilizations out of the galaxy. The real estate is abundant. The chemistry works. Life begins quickly. Intelligence might be rare, but not impossible. And yet, across 13.6 billion years and hundreds of billions of stars, the result is zero. In 1996, an economist looked at this exact problem and gave the bottleneck a name. Robin Hanson was not an astronomer. He was not a physicist. He was an economist at George Mason University, and in 1996, he published a paper that reframed the Fermi Paradox in terms that a betting market would understand. His reasoning went like this. Between dead rock and a galaxy-spanning civilization, there is a long chain of steps, forming a planet, developing life, evolving complex cells, producing intelligence, building technology, surviving long enough to expand. If the galaxy should be full of civilizations but is not, at least one of those steps must be extraordinarily unlikely. A bottleneck so severe that almost nobody gets through. Hansen called it the Great Filter. The concept is pure probability. You do not need to know which step is the hard one. You just need to accept that the silence proves a filter exists somewhere in the chain. The math requires it. If every step were reasonably probable, the galaxy would be visibly colonized. It is not. Therefore, at least one step has a near-zero pass rate. The critical question is not whether the filter exists. The silence answers that. The critical question is where it sits. And this is where the concept becomes personal. If the great filter is behind us, somewhere in the early steps, then we already passed it. Maybe the origin of life is the hard part, and we got lucky. Maybe the jump from single-celled organisms to complex multicellular life is nearly impossible, and Earth just happened to clear that hurdle. If the filter is behind us, we are rare but safe. The hard part is over. If the great filter is ahead of us, somewhere in the later steps, then every civilization that reaches our level of technology eventually hits a wall it cannot survive. Nuclear war, environmental collapse, engineered pandemics, something we have not even imagined yet. Under this scenario, the silence is a graveyard. Every civilization that got as far as we have is dead or dying. Hansen laid this out as a binary, behind or ahead, lucky or doomed, and for years, the optimists had the stronger case. The emergence of complex life does appear to be genuinely difficult. Earth spent roughly 2 billion years stuck at the single-celled stage before the jump to multicellular organisms. Intelligence took another 2 billion years after that. These are long timescales, and the probability at each transition might be extremely low. It seemed plausible, even likely, that we had already cleared the hardest steps. To make the stakes concrete, imagine 100 civilizations starting the journey from simple chemistry to interstellar travel. If the filter is behind us, 99 of them never get past microbial life, and we are the one that did. Dangerous, but done. If the filter is ahead, all 100 develop technology, and 99 are destroyed before they can leave their home planet. We have built the rockets. We have built the radio telescopes. We have not yet crossed whatever line kills the others. For 2 decades after Hansen's paper, the debate stayed roughly balanced. Good arguments on both sides, no decisive evidence either way. Then, in 2024 and 2026, 2 papers landed that shifted the weight sharply toward the worst-case scenario. Both proposed filters ahead of us, and both described mechanisms that are already underway. Michael Garrett is an astrophysicist. In 2024, he published a paper proposing that artificial intelligence is the great filter. His argument was built on a timeline. Earth's first radio transmission occurred in 1895, when Guglielmo Marconi sent signals across a distance of about 1.25 miles. 127 years later, in 2022, generative artificial intelligence systems began operating at a level that surprised even their creators. The jump from first radio wave to sophisticated AI took just over a century. Garrett's model assumes that any technological civilization follows a similar trajectory because the underlying pressures are the same. Once you develop electronics, the path toward increasingly autonomous computing systems is not optional. It is driven by economic competition, military advantage, and the basic logic of tool improvement. Garrett's estimate for the window between developing artificial intelligence and being destroyed or fundamentally altered by it is roughly 200 years, not thousands. Not millions, 2 centuries. That is the total duration during which a civilization might be broadcasting detectable signals while still existing in a form that would produce those signals. Apply that window to the Milky Way. The galaxy is 13.6 billion years old. A civilization's detectable phase lasts 200 years. That is like trying to photograph a specific lightning bolt during a storm that lasts 4 million years. Even if millions of civilizations have arisen across the galaxy's history, the probability that any 2 of them overlap in their 200-year windows is vanishingly small. The model does not require AI to physically destroy a civilization. It also accounts for scenarios where AI transforms a civilization into something unrecognizable. A species that merges with its machines, or is replaced by them, or stops broadcasting because the AI has no interest in radio communication. The observable signature disappears. The civilization goes dark. Look at Earth's own trajectory. Military radar, the loudest signal we produce, operates at roughly 10 to the 14th watts in directional bursts. Those signals are detectable by a Green Bank-class telescope up to about 200 light-years away. But we are already shifting toward fiber optics, compressed digital transmissions, and tight beam communication that does not leak into space. Earth is getting quieter. Within a few decades, our unintentional radio emissions may drop below the detection threshold of any realistic alien telescope. We are closing our own window from the inside. To put 200 years in physical terms, imagine the entire history of the Milky Way as a single mile-long road. 200 years is roughly 1/5 of 1 inch. That is the stretch of pavement during which any given civilization is broadcasting. The rest of the mile is silence, before and after. Garrett's paper was not the only one to propose a filter ahead of us. In February of 2026, a researcher proposed something that does not require machines at all. Darren J. Duggan proposed a different mechanism for civilizational extinction. His filter does not require machines turning against their creators. It does not require war or asteroid impacts or any external catastrophe at all. It requires only one thing: a species smart enough to decouple reproduction from survival. And it is already measurable in the demographics of every industrialized nation on Earth. Birth rates are falling across the developed world as a direct consequence of prosperity and choice. Duggan's model treats this as universal, an inevitable property of any species intelligent enough to control its own fertility. The question his paper asks is whether any civilization can reverse the trend before the math becomes irreversible. The math is already moving. South Korea's total fertility rate in 2024 was 0.72. That means, for every 2 adults, fewer than 1 child. Replacement level is 2.1. South Korea is not at half replacement, it is at 1/3. Japan is at 1.2, Italy at 1.24. China dropped below replacement in 2022 and is accelerating downward. The United States fell below replacement in 2021. These are not projections, these are census numbers. Duggan's model does not treat fertility decline as a crisis to be solved. He treats it as a thermodynamic inevitability, the same way entropy is inevitable. His argument works like this. In any species that evolves intelligence, individuals eventually gain the ability to choose whether to reproduce. Once that choice exists, the calculus shifts. Children become expensive in time and resources. In a subsistence society, children are labor. In a technological society, children are cost. Every government that has tried to reverse the trend has failed. Pronatalist policies in Scandinavia, in Japan, in Singapore, in Hungary, have produced temporary bumps of a few percentage points before the decline resumed. France, which has the most generous family support system in Europe, still fell below replacement. Duggan's projection maps current global trends forward. Human population peaks around 2080 at roughly 10 billion, then begins a decline that accelerates with each generation. By 2500, his model estimates fewer than 100 million humans on Earth. By 3000, functional extinction. A species that once covered a planet, gone, dissolved into empty maternity wards. The physical comparison is bacterial, a petri dish colony that consumes all nutrients and dies. But Duggan's filter is worse than starvation. In the petri dish, the bacteria run out of food. In his model, the food is still there. The civilization simply stops eating. And if this is universal, if every intelligent species that gains control over its own reproduction follows the same curve, it explains the silence without invoking catastrophe. No nuclear war, no asteroid, just a slow, quiet fade across every inhabited world in every galaxy. Civilizations rise, develop technology, decouple sex from reproduction, decouple reproduction from survival, and dissolve over a few hundred generations. The galaxy fills with ruins, not conquerors. 2 filters, then, Garrett's artificial intelligence window of 200 years and Duggan's depopulation curve of 500 to 1,000 years. These are not mutually exclusive. A civilization could face both simultaneously, and both papers were published within 2 years of each other. based on trends already visible in human data. For decades, the optimistic view held that the Great Filter was behind us. The hard step was the origin of life, or the jump to multicellular complexity, or the emergence of intelligence. We had already cleared those hurdles. The new evidence says otherwise. The filter is ahead of us, and we are inside the danger zone right now. But both of these filters assume civilizations destroy themselves or fade away. There is another possibility that nobody talks about as much, because it does not involve death at all. What if civilizations do not die? What if they just go quiet? Here is a fact that undermines the entire premise of the search for extraterrestrial intelligence. Earth is getting quieter. In the 1960s and 70s, humanity was loud. Omnidirectional radio broadcasts, television signals, and military radar systems pumped electromagnetic radiation into space in every direction. Military radars, the loudest signals Earth produces, peak at roughly 10 to the 14th watts when measured directionally. A telescope the size of Green Bank, 100 meters across, could detect those signals from about 200 light-years away. That sounds like a lot. It is not. 200 light-years covers roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. Our loudest screams reach 0.000004% of the galaxy, and we are getting quieter every year. Fiber optic cables carry data through glass, not through the air. Cellular networks use low-power transmitters aimed at the ground, not the sky. Digital signals are compressed and encrypted, which makes them look indistinguishable from random noise to a distant receiver. Military radar is shifting to phased arrays that focus energy in tight beams rather than spraying it everywhere. Earth, in 1970, was a bonfire visible from miles away. Earth in 2026 is a flashlight pointed at the floor. Seth Shostak at the SETI Institute has been making this argument for years. Advanced civilizations are not louder than primitive ones. They are quieter. A civilization 1,000 years ahead of us might communicate entirely through tight beam lasers, quantum encrypted channels, or technologies we have not invented yet. Their communications would be invisible to us because efficiency naturally selects for directed, low-waste transmission. Think of it like mail delivery. A medieval town crier shouts announcements in the square. Everyone within earshot hears it. A modern postal system delivers letters to specific addresses. The information flow increased by orders of magnitude, but the noise dropped to nothing. A civilization using tight beam communication could be exchanging more data in 1 second than humanity has broadcast in its entire radio history, and we would never know. An alien civilization monitoring Earth from 500 light-years away in 1970 would have picked up our television signals. The same civilization monitoring Earth in 2070 might detect nothing at all. We would look dead. And this applies in reverse. A civilization 500 light-years away that went through the same technological transition 500 years ago would already be invisible to us. We would point our telescopes at their star and hear silence because they upgraded their infrastructure. The entire logic of SETI, listening for electromagnetic leakage, depends on catching civilizations during a narrow window, when they are technologically advanced enough to broadcast, but not yet efficient enough to stop leaking. That window might be 100 years, maybe 200. On a cosmic timeline of 13.6 billion years, 200 years is nothing. It is a camera shutter click. Two civilizations would both need to be in their leaky phase at the same time, pointed at each other, within detection range. The probability of that overlap drops with every decade a civilization becomes more efficient. So perhaps the silence is evidence of graduation. But some scientists were not satisfied with just listening for leakage. They wanted to look for something bigger, something physical you could see across the entire galaxy. In 2024, a project called Hephaistos published results that made international headlines. The team had scanned approximately 5 million stars within 300 parsecs, roughly 1,000 light-years, looking for something no one had ever systematically searched for at that scale: Dyson spheres. The concept goes back to the physicist Freeman Dyson in 1960. A sufficiently advanced civilization, he argued, would eventually need more energy than a single planet could provide. The logical next step would be to build a structure around its star, a shell or swarm of collectors that captures the star's entire energy output. Such a structure would not be invisible. The laws of thermodynamics guarantee it. It would absorb visible light from the star and re-emit that energy as infrared radiation, waste heat. No matter how advanced the engineering, waste heat cannot be eliminated entirely. From a distance, a star surrounded by a Dyson sphere would look dimmer in visible light and brighter in mid-infrared. That is exactly what Hephaestus found. 7 M-dwarf stars showed anomalous mid-infrared excess that could not be easily explained by known astrophysical processes. M-dwarfs are small, cool, long-lived stars, the most common type in the galaxy. They are also the most energy-efficient targets for a megastructure project because they burn for trillions of years, far longer than stars like ours. A civilization that wanted to build for permanence would choose an M-dwarf for the same reason you would build a house on stable ground rather than a floodplain. The 7 candidates passed multiple filters. The infrared excess was real. It was measured. It was consistent with what a partial Dyson sphere, one that does not fully enclose the star, would produce. The paper was careful to list natural explanations like circumstellar dust or debris disks, but noted that none of them fully accounted for the observed spectral shape. The infrared profile did not match any standard model of stellar dust. Something unusual was going on around those 7 stars. The response was immediate. News outlets ran headlines about possible alien megastructures. Social media exploded. The paper accumulated hundreds of thousands of views within weeks. For a brief window, the scientific community allowed itself to consider the possibility that someone, somewhere, had built something around a star. To understand the scale of what a Dyson sphere would represent, consider this. Earth intercepts roughly 1/1000th of our star's total energy output. A complete Dyson sphere would capture all of it, an increase in available energy by a factor of 1 billion. A civilization with that much energy could do things we cannot currently imagine: power interstellar transmitters visible across the galaxy, run computational systems the size of planets, even physically reshape their solar system. For comparison, the total energy output of every power plant on Earth combined is roughly 10 to the 13th watts. A Dyson sphere around a star like ours would produce roughly 3.8 times 10 to the 26th watts. The gap between human civilization and a Dyson sphere civilization is 13 orders of magnitude. That is why the Hephaestus result mattered. It was a physical measurement of actual infrared light from actual stars behaving in ways that were hard to explain. The team was cautious. They did not claim they had found aliens. They claimed they had found anomalies worth investigating. But within months, those anomalies would have a very different explanation, and it would be one that nobody involved in the original search had anticipated. The follow-up analysis came in 2025. Independent teams re-examined the 7 M-dwarf candidates using additional infrared and optical data. What they found was not alien megastructures. It was background contamination. The anomalous infrared excess was real. It just was not coming from the stars. It was coming from objects behind them, billions of light-years further away. Dust-obscured galaxies, known in the literature as DOGs, and active galactic nuclei, the supermassive black holes at the centers of distant galaxies that spew enormous amounts of energy as they consume surrounding matter. These background sources happen to sit along the same line of sight as the M-dwarf candidates. Their infrared emissions blended with the starlight, creating the illusion that the stars themselves were producing excess heat. The resolution of the original survey was not fine enough to separate foreground stars from background galaxies at those angular scales. Once higher resolution data was applied, separating the faint background glow from the foreground starlight, the megastructure signatures disappeared. The stars were ordinary. The infrared excess belonged to objects that had nothing to do with them. The universe had done it again. It had perfectly mimicked the signature of advanced technology, using nothing but random cosmic geometry and hot dust. This was not the first time. In 1967, Jocelyn Bell Burnell detected a signal so regular that her team labeled it LGM1, Little Green Men. It was a pulsar, a rotating neutron star. In 1977, the WOW signal matched every criterion for an artificial extraterrestrial transmission. Decades of analysis now point to a natural origin, likely a magnetar-triggered hydrogen maser flare from interstellar gas along the line of sight. In 2020, BLC-1 looked exactly like a signal from Proxima Centauri. It was electronics near the Parkes telescope. Now, in 2024, 7 stars looked exactly like partial Dyson spheres. They were background galaxies. The pattern is consistent, and it is uncomfortable. Every time we think we have found something, nature offers a natural explanation that nobody predicted beforehand. The universe is actively deceptive. It produces phenomena that look engineered, that pass our filters, that survive initial scrutiny, and then collapse into mundane physics when examined more closely. A Dyson sphere search covering 5 million stars, the largest ever conducted, reduced to zero by dust and geometry. 5 million stars, and not one megastructure, not one hint of engineering at any scale. The physical analogy is a mirage on a highway. On a hot day, the road ahead appears to be covered in water. The light is real, the bending is real. The physics producing the illusion is real. But the water is not there. You can drive toward it forever and never reach it. The Hephaistos result was a cosmic mirage, 7 candidates, all explained by geometry and distance. And it raises a question that sits beneath all of SETI. If the universe keeps producing false positives that fool our best instruments, how confident can we be in our ability to recognize a true positive if one ever appears? The answer, increasingly, is not very. But false positives and cosmic mirages are one category of explanation for the silence. There is a darker one. What if the civilizations are out there, and they are real, and they are staying hidden on purpose? In 2008, the Chinese science fiction writer Liu Cixin published the second novel in his 3-body trilogy. It was called The Dark Forest. The book proposed an answer to the Fermi Paradox that was elegant and deeply disturbing. It went like this. The universe is full of civilizations. They are all silent because revealing your location is the same as committing suicide. The logic builds from 2 axioms. First, survival is the primary need of every civilization. Second, civilizations continuously grow and expand, but the total matter and energy in the universe does not. These 2 axioms produce a problem. Resources are finite. Civilizations are potentially infinite. Any civilization that encounters another faces a choice: cooperate or destroy. But cooperation requires trust, and trust requires communication, and communication reveals your position. Here is where the game theory becomes lethal. You cannot verify another civilization's intentions. They might be peaceful today and hostile in 1,000 years. They might be technologically inferior today and superior in a century. The only way to guarantee your safety is to strike first, before the other civilization becomes a threat. And because every civilization knows this, every civilization that has survived long enough to exist right now has learned the same lesson. Stay quiet, stay hidden, shoot anything that makes noise. Liu Cixin called this the dark forest. Picture a forest at night. It is full of hunters. Every hunter knows the forest is full of other hunters. No one can see more than a few feet. Every sound, every movement, could attract a bullet. The rational strategy is to stand perfectly still and shoot at any noise. The cosmos, in this model, is packed with armed civilizations standing motionless in the dark. The hypothesis has a specific physical implication. A dark forest civilization would not build Dyson spheres, because Dyson spheres are visible across the galaxy. It would not broadcast radio signals, because radio signals reveal location. It would not expand aggressively, because expansion creates a detectable footprint. It would minimize its observable signature in every possible way. It would look, from the outside, exactly like the silence we observe. The idea was not entirely new. John Bohr proposed the zoo hypothesis in 1973, suggesting advanced civilizations might deliberately avoid contact with primitive species, the way a nature reserve keeps humans away from endangered animals. The dark forest takes this further. They avoid detection out of survival. Critics of the dark forest hypothesis point to several problems. It assumes a level of paranoia that may not be universal. It requires that every civilization independently arrives at the same conclusion, with no exceptions, because even one loud civilization would break the silence. It also assumes that destroying a distant civilization is easier than communicating with one, which is not obviously true given the distances involved. But the hypothesis has one property that makes it impossible to fully dismiss. It is consistent with the data. The silence is exactly what a dark forest universe would look like. And it leads directly to a real controversy happening right now on Earth, one that has split the scientific community and involves the question of whether we should be shouting into that forest. In 1999, a Russian astronomer named Alexander Zaitsev did something that no international body had approved and no scientific consensus had endorsed. He used the Evpatoria planetary radar facility in Crimea, a dish originally built for deep space communication with Soviet probes, to transmit a high-powered, targeted message towards several nearby star systems. He called it Cosmic Call. The transmission was designed to be detectable by any civilization with a radio telescope comparable to our own. It contained mathematical and scientific information encoded in a format meant to be decipherable by any technologically capable species. Zaitsev did not consult the SETI community before transmitting. He did not seek approval from any government. He did not ask for international review. He did not need to, because there is no binding international protocol governing deliberate transmissions into space. None. There are guidelines. The International Academy of Astronautics has a set of recommendations, but they are voluntary. No treaty, no law, no enforceable agreement prevents anyone with access to a sufficiently powerful transmitter from broadcasting a message into the cosmos right now, today, announcing humanity's existence and location to anyone listening. The reaction within the scientific community was immediate and bitter. David Brin, the physicist and author who had written extensively about the Fermi Paradox, called it reckless and potentially catastrophic. If the dark forest hypothesis had even a small probability of being correct, Brin argued, deliberately transmitting was the equivalent of lighting a bonfire in a forest full of predators. Brin resigned from SETI-affiliated committees in protest over what he saw as a complete absence of governance over active messaging, which the community calls METI, Messaging to Extraterrestrial Intelligence. Jill Tarter, who had spent 35 years directing SETI searches, including Project Phoenix, and who was the real-world inspiration for the character in the film Contact, found herself caught in the middle. She supported the search for signals, but had reservations about transmitting. Dan Wertheimer, a Berkeley astronomer, argued that any deliberate transmission should require global consensus. The idea of one person, or one country, making a decision that could affect the entire species struck him as unacceptable. Seth Shostak, at the SETI Institute, took the opposite view. His argument was practical. Earth's military radar systems have been leaking detectable signals into space for decades. Anyone within 200 light-years who has the technology to threaten us already knows we are here. Deliberately transmitting changes nothing. Hiding is pointless because we never were hidden. Think of it this way. You are standing in a dark room and you have been coughing loudly for 70 years. Someone suggests that maybe you should stop coughing, but you have been coughing the entire time. If something in the dark wanted to find you, it already has. The debate has never been resolved. It cannot be, because the underlying question is unanswerable. Is the universe dangerous or not? And the split reveals something that most people assume about science, but is wrong. People assume that the scientific community coordinates its relationship with the cosmos, that there are protocols and oversight and institutional control over what humanity says to the stars. There is not. The METI controversy proved that any individual with the right equipment can speak for the entire species. And whether or not anyone is listening on the other end, the tools we have built to find out keep getting destroyed. On December 1st, 2020, the 900-ton receiver platform of the Arecibo Observatory broke free from its cables and crashed through the 305-meter radio dish below. The collapse was not sudden. Engineers had been warning about cable degradation for months. 2 cables had already failed in August and November. The National Science Foundation made the decision not to attempt repairs because sending workers onto the structure was too dangerous. When the platform fell, it destroyed the dish, the instrument that had been the largest single-aperture radio telescope in the world for 53 years. The NSF chose not to rebuild. Arecibo had been used for SETI at home, Project Phoenix, radar mapping of near-Earth asteroids, pulsar research, and atmospheric studies. It was one of the most scientifically productive instruments ever built, and it was gone. But Arecibo was not the first. The Big Ear Telescope in Ohio, the instrument that captured the WOW signal in 1977, was demolished between 1997 and 1998, so the land could be developed into a golf course. The most promising candidate signal in the history of SETI, and the telescope that found it was paved over for a driving range. The Allen Telescope Array, a field of 42 dishes in Northern California, designed specifically for SETI, was built as a joint project between the SETI Institute and the University of California at Berkeley. Each dish is 6 meters in diameter, operating across 1 to 14 gigahertz. In 2011, the array went into hibernation. The reason was money. The SETI Institute could not afford $1.5 million a year to keep it running. For context, a single F-35 fighter jet costs $80 million. The array was later reactivated with private funding, but the hibernation period illustrated a pattern. Then, there is the federal funding history. NASA's first dedicated SETI program, the High-Resolution Microwave Survey, launched in 1992 with a $12 million annual budget. It combined a targeted search using Arecibo with an all-sky survey using the Goldstone Deep Space Network dish. Senator William Proxmire had already killed an earlier NASA SETI effort in 1981 by giving it his Golden Fleece Award, a prize he invented for what he considered wasteful government spending. Carl Sagan personally lobbied Proxmire and convinced him to reverse his position. But in 1993, Senator Richard Bryan of Nevada permanently defunded the program. It had been running for 1 year, $12 million. That is roughly the cost of 600 feet of interstate highway. Since 1993, every major SETI effort has been privately funded. The search for the answer to one of the most fundamental questions humanity has ever asked, are we alone, depends entirely on the generosity of individual donors and the occasional billionaire. The pattern is hard to ignore. The telescope that found the best signal was demolished for real estate. The telescope array built for the search was shut down over pocket change. The federal program was killed for politics, and the largest radio dish in the Western Hemisphere was allowed to collapse and was never rebuilt. If you were designing a civilization that would never detect an extraterrestrial signal, this is roughly how you would do it. In 2015, a Russian-Israeli billionaire named Yuri Milner stood on a stage in London alongside Stephen Hawking and announced Breakthrough Listen, $100 million over 10 years dedicated to the most thorough search for extraterrestrial intelligence ever attempted. It was the largest single injection of funding in SETI history. Milner also announced Breakthrough Starshot, another $100 million aimed at developing technology to send gram-scale probes to the nearest star systems at 20% of light speed. Breakthrough Listen gained access to some of the most powerful radio telescopes on Earth. Green Bank in West Virginia, 100 meters in diameter, the largest fully steerable radio dish in the world. Parkes in Australia, 64 meters, one of the most sensitive radio instruments in the Southern Hemisphere. Meerkat in South Africa, an array of 64 dishes designed for the next generation of radio astronomy. And the Automated Planet Finder at Lick Observatory in California, a 2.4-meter optical telescope capable of detecting laser pulses from distant civilizations. The strategy was simple in concept. Point the best instruments at the most promising targets and listen at every frequency simultaneously. By 2024, the project had scanned approximately 1 million nearby stars. It had accumulated more than 2 petabytes of data, a volume that would fill roughly 400,000 DVDs. Its sensitivity was extraordinary. Breakthrough Listen could detect a transmitter producing 10 to the 12th to 10 to the 13th watts, roughly equivalent to the total power output of a small nuclear power plant from nearby star systems. Any civilization within a few hundred light years that was broadcasting at those power levels would show up in the data. To put that sensitivity in perspective, it means Breakthrough Listen could detect the equivalent of a single large television transmitter from a planet orbiting the nearest 1,000 stars. If anyone nearby was making any deliberate effort to be heard, these instruments would have caught it. Nothing did. 2 petabytes of silence. 1 million stars surveyed. Thousands of hours of observation time across 4 major instruments on 3 continents. The result was the same result SETI has gotten since Frank Drake pointed the 85-foot Tetzel telescope at Tau Ceti in 1960. 0. But then, in 2020, one of Breakthrough Listen's own instruments caught something that made the entire team hold its breath. Parkes, the 64-meter dish in New South Wales, detected a narrowband signal at 982.002 MHz. Narrowband signals are significant because natural astrophysical sources almost always produce broadband emissions, energy spread across a wide range of frequencies. A narrowband signal, concentrated at a single frequency, is one of the hallmarks of an engineered transmission. And this one appeared to come from the direction of Proxima Centauri, the nearest star to our own, 4.24 light-years away, a star already known to have at least 2 planets, one of which sits in the habitable zone. The signal was designated BLC-1, Breakthrough Listen Candidate 1. It was the first signal the project had ever considered promising enough to earn a formal candidate designation, and for the scientists involved, the months that followed were some of the most intense in modern SETI history. BLC-1 drifted in frequency. That mattered. When a signal comes from a source on a rotating planet, the rotation causes a Doppler shift, a gradual change in the observed frequency. Earth-based interference does not typically drift in the same way because the transmitter and receiver are on the same rotating body. BLC-1's drift rate was consistent with what you would expect from a transmitter on a planet orbiting Proxima Centauri. The signal appeared only when the telescope was pointed at Proxima Centauri. When the dish moved to observe a reference direction away from the star, the signal vanished. When it swung back to Proxima, the signal returned. This on-off pattern is the standard test for distinguishing celestial signals from local interference. BLC-1 passed it. For months, The Breakthrough Listen team worked in near secrecy. They reprocessed the data. They checked for known sources of interference. They cross-referenced with databases of terrestrial transmitters, satellites, aircraft, and ground-based electronics. They applied every filter in their pipeline. BLC-1 survived them all. Word eventually leaked to the press in late 2020. The story made international news. Scientists who had spent decades managing public expectations about SETI found themselves being asked a question they had always hoped to answer, but never expected to face this directly. Is this it? It was not. In 2021, the Breakthrough Listen team published a thorough analysis showing that BLC-1 was almost certainly human-generated radio frequency interference. The key evidence was the discovery of structurally similar signals at nearby frequencies, signals that shared the same characteristics as BLC-1 but came from directions that had nothing to do with Proxima Centauri. The most likely source was electronics operating near the Parkes telescope itself, intermodulation products created when multiple radio frequency sources interact and produce spurious signals at new frequencies. The drift rate that had seemed so convincing turned out to be within the range producible by local interference under certain conditions. The value was not unique to a planetary source. The on-off pattern could be explained by the telescope's side lobes, secondary sensitivity lobes outside the main beam, picking up local signals only at certain pointing angles. BLC-1 was electromagnetic noise from approximately 0 light-years away. The most exciting SETI candidate in decades had been generated by human technology sitting within the telescope compound itself. Imagine hearing a knock at your door in the middle of the night. You check the peephole. Nobody. You open the door. Nobody. You step outside and hear the knock again and realize it is coming from the pipes inside your own wall. BLC-1 was the knock in the pipes. The disappointment went deeper than emotion. It was methodological. BLC-1 demonstrated that even the most sophisticated SETI pipeline in the world, backed by $100 million in funding and decades of expertise, could be fooled by a signal originating a few hundred feet from the telescope. If local interference can mimic every characteristic of an extraterrestrial transmission, the bar for a confirmed detection is effectively unreachable with a single instrument. Any credible claim would require simultaneous confirmation from multiple independent telescopes on different continents, observing the same signal at the same time and ruling out every possible terrestrial source independently. BLC-1 joined the WOW, Signal, and the Dyson Sphere candidates on a growing list of things that almost were but were not. And while Breakthrough Listen was chasing a ghost from next door, a new generation of instruments had begun the largest systematic search ever conducted. The results were already in, and they were the same. In March of 2023, an instrument called COSMIC came online at the Very Large Array in New Mexico. The VLA is an icon of radio astronomy, 27 dishes spread across the desert in a Y-shaped configuration, each dish 25 meters in diameter. COSMIC, which stands for Commensal Open Source Multimode Interferometer Cluster, does something no previous SETI instrument had done at this scale. It piggybacks on normal astronomical observations. Whatever the VLA is pointed at on any given night, COSMIC processes the same data in parallel, searching for narrowband signals that might indicate a technological source. This means COSMIC gets telescope time for free. It does not compete with other scientific programs. It simply watches everything the VLA watches and runs its own analysis on top. In its first 11 months of operation, COSMIC observed more than 950,000 unique fields, covering 267,510 individual stars. It searched across 2 to 4 gigahertz, a frequency range that includes the waterhole, the quiet band between the hydrogen line at 1,420 megahertz and the hydroxyl line at 1,665 megahertz, that has long been considered the most logical place for an intentional interstellar signal. The result from those 11 months: 0 techno-signatures. COSMIC was not the only large-scale search running. In 2024, the Murchison Wide Field Array in Western Australia, a low-frequency radio telescope, surveyed 2,800 entire galaxies for techno-signatures, not stars, galaxies, each containing hundreds of billions of stars. The logic was that a sufficiently advanced civilization, one that had achieved galaxy-spanning engineering, might produce signals detectable across intergalactic distances. The MWA found nothing. In October of 2024, the Allen Telescope Array conducted the longest continuous SETI observation ever aimed at a single target. 28 hours pointed at TRAPPIST-1, a red dwarf star, 39 light-years away that hosts 7 rocky planets, 3 of which sit in the habitable zone. The search produced 2,264 candidate signals. Every single one was traced to terrestrial origin. Then, in July of 2025, something entered the solar system from interstellar space. 3I, Atlas, the third confirmed interstellar object ever detected, following Oumuamua in 2017 and Borisov in 2019. The ATA pointed at it within days. Over 7.25 hours of observation, the array recorded 74 million narrowband hits. Automated filters reduced that to 211 candidates worth a closer look. The final number, 0. 74 million signals from the direction of an object that came from another star system. Not one was artificial. The searches are orders of magnitude larger than anything Frank Drake could have imagined when he pointed his 85-foot dish at 2 stars in 1960. The instruments are more sensitive. The frequency coverage is broader. The analysis is faster, with artificial intelligence accelerating Breakthrough Listen's data processing by a factor of 600. And the number has not changed. It was 0 in 1960. It was 0 after 1 million Breakthrough Listen stars. It was 0 after 950,000 cosmic fields and 74 million narrowband hits from an interstellar visitor. At some point, the absence of evidence starts to become evidence of absence. And that forces a question that the next chapter of this investigation cannot avoid. For decades, there was a standard defense against the silence. Jill Tarter, who spent 35 years directing the search for extraterrestrial intelligence, put it this way: imagine you want to know if there are fish in the ocean. You walk to the shore, scoop up a single hot tub of water, look inside, and find nothing. Would you conclude the ocean has no fish? That was the argument. All of SETI's searching, every dish pointed at every star, every frequency scanned, every algorithm run, amounted to a hot tub of water scooped from a cosmic ocean. Less than 1% of the sky has been searched at the frequencies and sensitivities that matter. Earth's radio bubble, the sphere of electromagnetic signals leaking outward from our planet, covers roughly 15,000 stars. The Milky Way contains somewhere between 200 billion and 400 billion stars. We are invisible to 99.99999% of the galaxy. The hot tub argument sounds reasonable. It sounds humble, and for a long time, it was enough to keep the question open without forcing uncomfortable answers. But it has stopped working. The problem is cumulative data. SETI at home ran for 21 years. Volunteers on millions of computers processed 12 billion candidate signals. Breakthrough Listen scanned approximately 1 million nearby stars and accumulated more than 2 petabytes of raw observations. The commensal open-source, multimode interferometer, networked search on the Very Large Array covered 950,000 unique fields in under a year. The Murchison Wide Field Array surveyed 2,800 entire galaxies. The Allen Telescope Array stared at TRAPPIST-1 for 28 continuous hours during planetary occultations, generating 264 candidates, all of which turned out to be terrestrial. Each of these programs used different instruments, different frequencies, different analysis pipelines, different parts of the sky. The combined result was always the same number. Statistical models built on 6 decades of null results now estimate fewer than 1 to 5 detectable technosignatures per century across the entire Milky Way galaxy. That is not a hot tub anymore. That is a measurement. The ocean has been sampled at enough points, with enough variety, over enough time, that the absence of fish is starting to tell you something real about the ocean itself. The shift is subtle, but it changes the entire investigation. For 60 years, the silence was treated as a gap in knowledge, a blank space waiting to be filled by better instruments or more patience. The new interpretation treats the silence as data in its own right, the way a blood test that comes back negative is still a medical result. 0 is not nothing. 0 is a finding, and that finding lands on the investigation like a weight, because it closes off the most comfortable exit. You cannot say we just have not looked hard enough. Not anymore. Not after 12 billion processed candidates and 74 million narrowband hits from an interstellar visitor all collapsing to the same number. The hot tub defense held for decades. It gave researchers permission to keep searching without confronting what the silence might mean. Now it is eroding under the sheer volume of nothing. And if the silence is real data, then the question changes shape entirely. It stops being about why we have not found anything yet, and becomes a question about what 0 actually means. That is a different kind of investigation, and it starts with the tools we thought we could trust to find life in the first place. There is a molecule that biologists have relied on for decades as a signpost for life: oxygen. Free molecular oxygen, the kind you breathe, is chemically reactive. It bonds with iron, carbon, silicon, iron, and dozens of other elements readily. Leave a planet alone for a few million years without something continuously replenishing the oxygen supply, and it vanishes from the atmosphere entirely. On Earth, that something is photosynthesis. Plants and cyanobacteria split water molecules apart using stellar radiation, release oxygen as a byproduct, and keep the atmosphere stocked at roughly 21% concentration. The logic seemed clean. If you point a telescope at a distant planet and detect free oxygen in the atmosphere, something biological is probably maintaining it because nothing else could. Oxygen became the gold standard biosignature. It was the single strongest indicator that a planet might host life. The James Webb Space Telescope was designed in part to do exactly this, to analyze the light filtering through exoplanet atmospheres and search for the chemical fingerprints of gases that should not exist without biology producing them. Entire careers were built around this assumption. Entire missions were justified by it. Then, in 2024, a team of researchers found oxygen being produced at the bottom of the Pacific Ocean, not by any living thing. The source was polymetallic nodules, lumps of metal ore sitting on the deep ocean floor at depths where no light from the surface reaches and photosynthesis is impossible. These nodules contain manganese, nickel, cobalt, copper, and other metals that generate small but measurable electrical voltages through natural electrochemical reactions. The voltage is enough to split seawater molecules into hydrogen and oxygen through a process called electrolysis. It requires no biology whatsoever. The researchers measured oxygen production rates that, in some areas of the abyssal plain, exceeded what the local microbial communities consumed. The deep ocean floor was generating more oxygen than the life around it was using. To put that in perspective, imagine discovering that the smoke detector you have relied on for your entire career also goes off randomly when nobody is cooking and nothing is burning. The alarm still functions, but now you cannot trust it to mean what you always assumed it meant. If oxygen can be produced without life on Earth, in Earth's own ocean, it can be produced without life on a rocky planet orbiting a red dwarf star 40 light-years away. One of the most foundational assumptions in astrobiology, that atmospheric oxygen equals biological activity, had developed a crack running through its center. This did not mean oxygen was useless as a biosignature. It meant oxygen alone was no longer sufficient evidence. You would need corroborating detections, other gases, other chemical patterns, an entire web of atmospheric signatures that together pointed toward biology rather than geology or chemistry. The problem is that the James Webb Space Telescope was already struggling to get even single biosignature detections from exoplanet atmospheres. Adding the requirement for multiple independent confirming signals from a single exoplanet atmosphere made an already difficult measurement harder by an order of magnitude. The telescope would need longer observation times, more transits, and better noise modeling for each target. And the one planet where the telescope thought it had found a second biosignature, something beyond oxygen, something that on Earth is produced almost exclusively by living organisms, turned out to demonstrate exactly how fragile the entire detection framework had become. The planet is called K2-18b. It orbits a red dwarf star 124 light-years from Earth. It is a sub-Neptune, meaning it is larger than our planet but smaller than Neptune, roughly 8.5 times Earth's mass. In 2023, the James Webb Space Telescope analyzed starlight passing through its atmosphere and detected what appeared to be dimethyl sulfide. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, the microscopic organisms floating in the upper layers of the ocean. It is the molecule responsible for the distinctive smell of the seaside. Finding it on another planet would be remarkable because there is no known geological or purely chemical process that generates dimethyl sulfide in significant quantities without biology. The headlines were immediate and global. Major news outlets reported the detection as potential evidence of biological activity on an alien world. For a brief window, K2-18b became the most discussed exoplanet in the scientific community and in popular media. Then the data was examined more carefully by independent teams. The dimethyl sulfide signal sat within the noise floor of the observation. The statistical confidence of the detection fell below the threshold that most scientists consider reliable for a formal discovery claim. Follow-up analyses using different atmospheric modeling approaches could not reproduce the result consistently. By early 2026, the scientific consensus had shifted. The signal was probably an artifact of the data reduction process, a ghost in the numbers rather than a molecule in the sky. As of this investigation, no exoplanet has a confirmed atmospheric biosignature. Not K2-18b, not any of the 7 worlds orbiting TRAPPIST-1, not the 756 planets confirmed by the Transiting Exoplanet Survey satellite, not the 2,783 worlds catalogued by Kepler. The next best candidate for atmospheric characterization is Gliese 12b, a rocky planet 9/10 the radius of Earth, sitting in a temperate orbit around its star just 40 light-years away. It is close enough and small enough that the James Webb Space Telescope could feasibly analyze its atmosphere over multiple observation cycles, building up signal over dozens of transits to push the detection confidence above the noise. Early characterization efforts are already scheduled, but after dark oxygen undermined one biosignature, and after K2-18b showed how a statistical artifact can briefly look like the discovery of a lifetime, the goalposts have moved. After dark, oxygen undermined one biosignature, and K2-18b exposed how easily another can emerge from statistical noise. The question is no longer just whether we will find the right planet. The question is whether we would recognize a genuine biosignature if it appeared in our data. A molecule that signals life on Earth might signal nothing but chemistry on another world. A detection that looks clean in one analysis might dissolve under a different statistical method. The tools are not broken, but the confidence we placed in them was premature. And there is a hypothesis, one that most working scientists refuse to take seriously, but none can formally disprove, that suggests the problem goes deeper than imperfect tools. It suggests we might not be seeing the real universe at all. In 2001, the science fiction writer Stephen Baxter published a thought experiment that most astronomers dismissed on sight, and none could actually refute. He called it the planetarium hypothesis. The idea is straightforward in its construction and disturbing in its implications. If a civilization existed that was sufficiently advanced, thousands or millions of years beyond our current technological level, it could enclose our solar system in a projected simulation, a perfect replica of an empty universe displayed inward from the boundary, so that every telescope, every satellite, every instrument humanity builds shows us exactly what the builders want us to see. We would observe an empty cosmos, because the cosmos we are permitted to observe is a constructed display. It sounds like science fiction because it originated in science fiction. Baxter was a novelist, not a physicist or an astronomer. But the hypothesis is a logical extension of an older idea proposed by the physicist John Ball in 1973. Ball called his version the zoo hypothesis. His argument was simpler. Advanced civilizations might deliberately avoid contact with primitive species, the same way a wildlife reserve keeps human visitors away from animals being studied. The animals in the reserve do not know they are being observed. They do not know the fence around the reserve exists. They simply live in what appears to be a natural environment, unaware that their natural environment has been curated. The planetarium hypothesis takes Ball's idea one step further. The advanced civilization does not merely avoid contact with us. It actively constructs the reality we observe. The fence is not around us. Everything we see is the fence. Scientifically, the hypothesis has a fundamental flaw that prevents it from being taken seriously in any formal sense. It is unfalsifiable. There is no observation you could make, no experiment you could design, no data you could collect that would prove you are inside a planetarium, because any evidence of the simulation could itself be a part of the simulation. That makes it bad science by any standard epistemological definition. It sits entirely outside the reach of the scientific method. But it is also logically consistent with everything we observe. Nothing in the laws of physics prevents a sufficiently advanced civilization from constructing such a projection. The energy requirements would be enormous, roughly equivalent to capturing the total output of a star, which is precisely what a Dyson sphere is designed to do. And the Dyson spheres we thought we found turned out to be background galaxies. Whether or not the planetarium hypothesis describes reality is beside the point. What it exposes is something uncomfortable about this entire investigation. Every explanation for the silence, the great filter, the dark forest, the zoo, the temporal coincidence argument, rests on the assumption that we are seeing the actual universe as it exists. If that assumption is wrong, every conclusion built on top of it collapses. The hypotheses are stacking up now. Filters that kill civilizations before they expand. Forests where civilizations hide from each other. Zoos where advanced species observe primitives. Planetariums where the observed reality is manufactured. Each answer raises new questions, and none of them are testable with current instruments. But there is one piece of hard evidence that cuts through all of this speculation, because it is not a hypothesis or a thought experiment. It is a measurement taken from our own planet's geological record, and it makes everything harder to explain. Life appeared on this planet almost immediately. Earth formed approximately 4.54 billion years ago from the gravitational accretion of dust and gas orbiting a young stellar system. For the first several 100 million years, the surface was largely molten rock. Asteroids bombarded it relentlessly during a period geologists call the Late Heavy Bombardment. Temperatures exceeded anything compatible with the complex chemistry of biology. Conditions were, by any reasonable standard, terrible for the emergence of living systems. Yet the last universal common ancestor, abbreviated LUCA, the single organism from which every living thing on Earth descends, bacteria, trees, fish, humans, existed approximately 4.2 billion years ago. That is a gap of somewhere between 300 and 400 million years between the planet's formation and the confirmed presence of life. And much of that window was spent under conditions where life, as we understand it, could not have survived on the surface. Life did not wait for perfect conditions. It did not require a billion years of slow chemical experimentation. It did not need a long sequence of improbable events lining up one after another. It started as soon as the planet cooled enough to sustain liquid water on its surface. To understand how fast that is in geological terms, imagine the entire 4.54 billion year history of Earth compressed into a single calendar year. The planet forms on January 1st. Life appears before the end of February. Dinosaurs do not show up until December. Humans arrive in the final minutes of December 31st. February. That is how quickly non-living chemistry transitioned to biology on this planet. If abiogenesis, the technical term for the process by which non-living matter becomes living matter, is that easy and that robust, then it should be happening on rocky planets throughout the galaxy right now and for billions of years before now. The 40 billion Earth-sized worlds, estimated to sit in habitable zones around stars in the Milky Way, are potential laboratories where the same chemical experiment has been running in parallel across billions of years. And yet intelligence took an additional 4.5 billion years to emerge on Earth after life appeared. Detectable technology, the kind that produces radio signals or infrared waste heat, appeared only in the last century. The bottleneck is clearly not life itself. Single-celled organisms, bacteria and archaea, and their equivalents, are probably common across the galaxy. They may be as ordinary as rocks. The bottleneck might not even be intelligence entirely, though the Stern and Guerrier estimate of 0.003 to 0.2% of life-bearing planets developing intelligent species makes that filter formidable. Earth itself spent more than 3 billion years populated exclusively by single-celled life before multicellular organisms appeared. That is not a brief delay. That is most of the planet's history. The real bottleneck might be something even further down the chain. Building a technological civilization that persists. Building something that does not collapse or fade, or go quiet before anyone in the neighborhood has a chance to notice it exists. That word, building, keeps surfacing in this investigation, and recent research into how life itself gets built suggests the path to biology might be even wider than anyone expected, which only makes the silence at the other end of that path harder to explain. For decades, the dominant theory about how life originated on Earth was called the RNA world hypothesis. The idea was elegant in its simplicity. Ribonucleic acid, a long-chain molecule that can both store genetic information and catalyze chemical reactions, somehow assembled itself from raw materials in Earth's primordial environment. Once it existed, it could copy itself. Copies introduced errors. Errors that happened to improve the molecule's ability to replicate were preserved. Natural selection, operating at the molecular level, took over from there. Eventually, over millions of years, RNA systems invented proteins, which were better at performing the chemical work of metabolism, and then DNA, which was more stable at storing genetic information long-term. Life, in this telling, began with a single type of molecule finding itself in the right chemical environment at the right moment. The RNA world was attractive because it solved biology's chicken and egg problem. Proteins need DNA to be coded. DNA needs proteins to be maintained. RNA can do both jobs, poorly but sufficiently, making it the plausible starting point. Research, published between 2023 and 2025 changed the picture substantially. Multiple independent studies demonstrated that amino acids, the chemical building blocks of proteins, and RNA nucleotides, the building blocks of RNA, likely co-evolved from the very beginning of prebiotic chemistry on Earth. They did not appear in sequence, one after the other. They appeared together, interacting in ways that made both components more chemically stable and more functionally capable than either would have been alone. Peptide RNA interactions, meaning short chains of amino acids physically binding to strands of RNA, drove the emergence of primitive genetic coding in two distinct stages. The first stage was purely chemical. Amino acids and nucleotides formed cooperative molecular systems, where each component stabilized the other against degradation. The second stage was informational. Those cooperative systems began encoding and transmitting rudimentary chemical instructions to daughter molecules, the distant ancestor of the genetic code used by every living cell on Earth today. Think of the difference this way. The RNA world model is like saying a car was built by first manufacturing a perfect engine, then adding wheels, then adding a frame. The coevolution model says the engine and frame all emerged together, each piece making the others possible. Life was not one molecule getting lucky. It was a system of molecules bootstrapping itself into existence. The distinction matters enormously for the Fermi Paradox. If the RNA world hypothesis was correct, abiogenesis depended on one specific molecule achieving one specific chemical configuration under one specific set of conditions. A tightrope, walk over a chasm. If the co-evolution model is correct, abiogenesis is more like a highway with multiple lanes and on-ramps. There are more chemical pathways that lead to living systems. The overall process is more robust and more tolerant of variation. Every revision to the origin of life story over the past 3 years has made biology look easier to start, more chemically probable, more likely to occur wherever conditions permit it. And every one of those revisions has made the silence more difficult to account for, because if the path from chemistry to life is a highway, and the universe has had 13.6 billion years to travel it, the complete absence of traffic at the destination requires an explanation that chemistry alone cannot provide. Something is halting the journey after it begins. Something happens between the emergence of biology and the emergence of a detectable signal. The question is what? And a mathematician who studies economics proposed an answer that reduces the problem to geometry. Robin Hanson built the Great Filter concept in 1996 as an economist's approach to the Fermi Paradox. 3 decades later, he extended the idea into something more specific and more testable. His grabby aliens model starts with a premise that sounds obvious, but has consequences that are not. If even a small fraction of technological civilizations decide to expand outward from their home star systems, traveling at even a modest fraction of the speed of light, they should be visibly reshaping the Milky Way galaxy by now. Obviously and visibly, a single civilization expanding at 1% of light speed, which is roughly 6.7 million miles per hour, would fill the entire galaxy in somewhere between 10 million and 100 million years. The Milky Way is 13.6 billion years old. There has been enough time for this expansion to happen thousands of times over. Hanson's mathematical model calculates what the galaxy should look like if expanding civilizations exist or have ever existed. They would convert stellar material and planetary resources into megastructures on a scale detectable across thousands of light years. They would harvest energy from stars in quantities that produce unmistakable infrared waste heat signatures. They would carve out spheres of influence, expanding bubbles of engineered space that astronomers could map the way cosmologists map the large-scale structure of the observable universe. The model predicts a galaxy that looks at least partially engineered, with visible boundaries between the territories of competing expansions stretching across hundreds or thousands of light years. The actual galaxy does not look like that. Not at all. Project Hephaestus surveyed approximately 5 million stars within 300 parsecs, roughly 1,000 light years. searching specifically for the infrared signatures that partial Dyson spheres would produce. 7 candidates emerged. All 7 turned out to be background contamination from dust-obscured galaxies billions of light-years behind the target stars. The Murchison Wide Field Array surveyed 2,800 entire galaxies at radio wavelengths for any sign of large-scale technological activity. The result was nothing. No megastructures anywhere. No expansion fronts. No engineered boundaries. No reshaping of any kind at any scale. The Milky Way looks precisely the way a galaxy would look if no technological civilization had ever built anything in it. Hansen's model provides an explanation for this. For our own existence to make statistical sense, for a species like humanity to have evolved without being overtaken by an expanding alien civilization first, technological civilizations must either be extraordinarily rare, or they must expand extraordinarily slowly, or something stops them before expansion begins. His calculations show that for multiple civilizations to coexist in the same galaxy without encountering each other, they would need average lifespans exceeding 280,000 years. For context, anatomically modern humans have existed for roughly 300,000 years total, and we have possessed technology capable of interstellar travel for exactly 0 of them. The evidence from recent research makes the lifespan requirement look impossible. Garrett's 2024 model gives civilizations roughly 200 years after developing artificial intelligence. Duggan's 2026 model gives them 500 to 1,000 years before demographic collapse. Neither comes close to the 250,000-year threshold that Hansen's geometry requires. The conclusion is stark. Civilizations do not expand because they do not last long enough to begin expanding. They appear, broadcast briefly, and vanish. The galaxy remains exactly as empty as it appears. But the investigation has one more lead to follow, because one instrument is still checking the last remaining candidates. In the mountains of Guizhou province in southwestern China, a natural limestone depression holds the largest single-dish radio telescope ever constructed. The 500-meter aperture spherical telescope, known by the acronym FAST, stretches 500 meters from edge to edge. If you placed it in downtown Manhattan, it would cover the distance from Wall Street to City Hall. FAST replaced the Arecibo Observatory as the world's most sensitive radio ear after Arecibo collapsed on December 1, 2020. Its 4,400 individual aluminum panels adjust in real time, giving it both enormous collecting area and the ability to track targets across the sky. Since July of 2025, FAST has been working through a specific list. When the SETI at Home distributed computing project shut down in March of 2020 after 21 years of operation, it left behind a legacy. Out of 12 billion candidate signals processed by volunteer computers worldwide, approximately 100 survived every stage of automated filtering. These were the signals that software could not classify as terrestrial interference, satellite contamination, or instrumental artifacts. They were anomalous enough that human researchers flagged them for follow-up with a more powerful instrument. FAST is that instrument. It is re-observing each candidate one by one, pointing its dish at the same celestial coordinates, tuning to the same frequencies, listening for any signal that repeats or matches the original detection profile. The process is methodical. Each target gets multiple observation sessions at different times to account for the possibility that a signal might be intermittent or directional. If even one of those candidates produces a confirmed repeat detection that cannot be attributed to terrestrial sources, the framework of this investigation changes overnight. As of early 2026, FAST has reported nothing from any of the re-observed candidates. The 100 signals that survived 21 years of distributed computing and billions of hours of volunteer processing appear to be dissolving under the scrutiny of a better telescope. Meanwhile, Machine learning algorithms developed for breakthrough listen now process radio telescope data 600 times faster than conventional methods. A dataset that would have taken a human team years to analyze can be filtered in days. The volume of sky being systematically searched per unit of time is growing exponentially compared to even 5 years ago. The Allen Telescope Array is being upgraded to cover frequencies up to 18 GHz. New commensal systems are being installed on radio telescopes across 4 continents. The search has never been faster, broader, or more sensitive. The result has not changed. The number at the end of every pipeline remains the same number it was in 1960, when Frank Drake pointed an 85-foot dish at 2 stars and heard nothing. There is a version of this story where FAST finds something genuine in the SETI at home leftovers. There is a version where the next breakthrough listen data release contains an anomaly that survives every verification test. Those versions are not impossible, but 65 years of consistent precedent makes a prediction about the next result, and it will be 0. That forces the question this investigation has been building toward since its opening, not where is everybody. Fermi asked that 76 years ago. The question now is what the answer means for a species still inside its own window. Start with what the evidence has established. 65 years of organized searching, Project OSMA to the commensal open-source multimode interferometer networked search, 12 billion candidates from SETI at home to 74 million narrowband hits from an interstellar object. Every candidate resolved to noise, interference, or a natural phenomenon nobody predicted. Every promising detection, pulsars in 1967, the WOW signal in 1977, BLC-1 in 2027, Dyson sphere candidates in 2024, dimethyl sulfide on K218b in 2023, either debunked or unconfirmed. The pattern is consistent. Every measurable variable in the Drake equation moved in a more optimistic direction since 1961. More stars have planets. Habitable zones are more common. Life starts faster than predicted. The count of Earth-sized habitable zone worlds went from a guess to 40 billion. Each revision should have made silence less probable. Instead, each made it more statistically significant, because the expected number kept climbing while the observed number stayed at 0. The filters stack, and each one narrows the funnel further. Intelligence requires a specific geological history, continuous plate tectonics for 500 million years, with a particular ratio of continent to ocean that fewer than 0.2% of life-bearing planets develop. Civilizations that reach technology face artificial intelligence within 2 centuries of their first radio transmission. Those that survive artificial intelligence face irreversible demographic collapse within 500 to 1,000 years as fertility rates drop below replacement and populations age beyond recovery. The detection window during which any civilization produces electromagnetic signals strong enough to cross interstellar distances may be as narrow as 100 years. Against 13.6 billion years of cosmic history, a 100-year detection window is a single water droplet falling into Lake Michigan. The instruments keep getting destroyed. Arecibo collapsed and was not rebuilt. Big Ear was demolished for a golf course. The Allen Telescope Array was mothballed for lack of $1.5 million a year, roughly 2 minutes of Pentagon spending. Congress killed NASA's SETI program twice. The biosignatures we trusted turned out to be less reliable than believed. Oxygen appears without biology. Dimethyl sulfide appears without statistical confidence. In 1999, a Russian astronomer named Alexander Zaitsev used the Yevpatoria planetary radar in Crimea to broadcast a targeted message toward nearby star systems. He did not consult any international body because no binding protocol required him to. The International Academy of Astronautics has guidelines. They are voluntary. Anyone with access to a sufficiently powerful transmitter can announce humanity's existence to the galaxy whenever they choose. And we would not know if something was listening until the reply arrived, traveling at the speed of light, decades or centuries later. The investigation does not conclude with a resolution. It concludes with a measurement. The universe has had 13.6 billion years and hundreds of billions of stars. On at least one planet, life started almost immediately and eventually produced a species that built radio telescopes and asked, "Where is everybody?" The silence is the information. Something about the journey from microbe to interstellar civilization is so difficult, so improbable, or so brief that in 13.6 billion years, it has either never been completed or never lasted long enough to leave a trace. That is not philosophy. That is what the data says, and it leads to one final, uncomfortable place. Earth has been broadcasting for roughly 100 years. The first radio signals powerful enough to leave the atmosphere date to the early 1920s. Military radar from the mid-20th century, peaking at around 10 to the 14th watts directional, is the loudest thing this planet has ever produced. Those signals expand outward at light speed in a sphere currently about 100 light-years across, containing roughly 15,000 stars. A civilization with a Green Bank-class telescope, 100 meters wide, aimed at our star during the right century, could detect us. But Earth is already getting quieter. The shift from broadcast television to streaming, from analog radio to digital compression, from omnidirectional radar to phased arrays, from open signals to encryption that looks like noise, all of it shrinks the footprint year by year. A civilization 1,000 years ahead of us might communicate through tight beam lasers or fiber optics, or something we cannot imagine. Their signals would disappear into the background. They would be invisible. Efficiency itself makes you silent. If Garrett's model is right, the window between first radio and artificial intelligence consuming a civilization is 200 years. Earth is 127 years in. If Duggan is right about demographic decline, the window stretches to 500 or 1,000 years. Take the generous number, 1,000 years of detectability in a galaxy 13.6 billion years old. That is a ratio of 1 to 13.6 million. For another civilization to notice us, it would need to exist at the same time, within range, with instruments pointed this way, tuned to the right frequency, during our window. We would need the same from them. The probability of two civilizations overlapping in both space and time is not zero, but it is small enough to explain the silence on its own. Two fireflies blinking in a forest the size of a continent. Each flash lasts a fraction of a second. Each firefly is real. They miss each other by 100,000 years and never know the other existed. In July 2025, the Allen Telescope Array tracked the third confirmed interstellar object through our solar system. 7.25 hours of listening, 74 million narrowband signals recorded, 211 candidates after filtering. Everyone came from Earth, somewhere around another star. Right now, an instrument may have scanned our system last week and found the same thing. Nothing. The silence does not prove we are alone. It is consistent with a universe where the window is small, the distances between stars are immense, and 13.6 billion years is not enough time for brief flashes of technology to overlap across a galaxy 100,000 light-years wide. The most common outcome may be the simplest one. Civilizations arise, broadcast for a geological instant, and go quiet. The galaxy could be full of ruins, or full of species that are silent by physics rather than by choice. It could contain thousands of civilizations that existed millions of years apart and never coincided. Any of those possibilities produces the same observable result: 0. FAST is still listening in Guizhou. The James Webb Space Telescope is still analyzing exoplanet atmospheres. Breakthrough Listen is processing data 600 times faster than 5 years ago. The question Enrico Fermi asked over lunch in 1950 has not been answered. The instruments are more powerful than they have ever been, and the window, whatever its true length, is still open.